We present partial correlation-based deep visual representation for image classification. Pairwise correlation-based representation, such as covariance matrix-based representation, has shown impressive performance in the recent years. Briefly, given CNN feature channels, the covariance computes pairwise correlation between different feature components. One of the key issues observed in pairwise correlation is confounding effect, which causes misleading correlation estimation. We propose partial correlation to remove the confounding effect. Partial correlation can be estimated by computing the inverse of covariance matrix. However, given the low spatial resolution and higher number of feature channels in recent CNNs, it is difficult to reliably estimate the inverse of covariance matrix. To improve this condition, we propose Sparse Inverse Covariance Matrix, or SICE in short. SICE can be computed by computing the displayed optimization problem with solvers such as CBXPy. However, those solvers do not support backpropagation. We propose an iterative method for obtaining SICE, which is integratable with CNN. Our method can be implemented directly with existing deep learning libraries, such as PyTorch, and can be optimized with gradient-based solvers, such as stochastic gradient descent. We have achieved state-of-the-art results on various datasets, such as CVP200 and Stanford cars. Now let's look at how iSICE can be integrated into CNN. Let's look at an example for a single image. Given that image, we use CNN to extract features in the form of a tensor. By reshaping the tensor, we compute sample-based covariance matrix. The sample-based covariance matrix is then used for computing sparse inverse covariance matrix using our proposed method. Since SICE is a symmetric positive definite matrix, we only use its upper triangular entries in the routine layers, such as softmax layer. iSICE has three hyperparameters, namely sparsity, number of iterations, and learning rate. While iSICE is robust to these hyperparameters, for better performance, optimal selection of these hyperparameters are important. We give a detailed discussion on this in our paper. We implement our method using PyTorch. We experiment with a large pool of network architectures, including the latest COMNext and Swing transformers. For all of our experiments, we used AdamW optimizer. We have used 8 datasets for evaluation of our proposed iSICE method. The datasets are MIT Indoor, CVP200, FGVC aircraft, Stanford cars, TDT, iNaturalist, Mini ImageNet, and ImageNet 100. We begin by experimenting on the iSICE hyperparameters across one scene and 3 fine-grained datasets, and 2 popular CNN backbones. We compare performance of iSICE with different combinations of these hyperparameters and select the optimal hyperparameters for different datasets. Here we show the performance of iSICE with various amounts of sparsity controlled by sparsity constant lambda. We repeat the same experiment for the learning rate and number of iterations. Please see our supplementary materials for their details. Upon obtaining the optimal hyperparameters, we rerun our experiments with iSICE and compare performance with its covariance counterparts, covariance matrix and precision matrix. We conduct experiments with large and medium-sized SICE matrices, and as you can see, across all experiments, iSICE performs better than 2 other methods across all datasets. We compare our method with state-of-the-art pairwise correlation-based methods. In the shown table, we see that our proposed method performs better than those state-of-the-art methods when paired with similar backbones. Since finding optimal hyperparameter for iSICE can be time-consuming, we also propose a simple method to learn those hyperparameters automatically with some simple MLP-based modulators. Using this scheme, one can learn essentially better performance. Please see our paper for more details. Our methods take a bit higher computation time than Newton-Schulz iteration-based covariance representation methods. However, it is not very high, and we do significantly better than original SICE with convex solvers. Now we visualize the learn feature by our iSICE method and compare them with its covariance counterparts and global average pooling. The feature map suggests that iSICE The model focuses well on the key parts of car to extract features for classification. Global average pooling overly focuses on entire foreground. I2T CUV focuses poorly, while iSICE let us control the degree of focus by controlling sparsity. Please visit our project website for more details and source code. Please scan the displayed QR code if you wish to avoid typing URLs. Thank you for listening, and I look forward to meeting you at CVPR.